Some discoveries refuse to let scientists sleep. High above us, the James Webb Space Telescope has been sending back images that bend old rules and whisper new questions into the dark. Galaxies that look too grown for a young universe. Structures that shouldn't exist so early. Light stretched from the edge of time, hinting that our cosmic story may be stranger and earlier than we thought. Tonight, on Fall Asleep to Astronomy, we'll drift toward these quiet disruptions, letting their mystery soothe rather than unsettle. No rush, no conclusions, only the soft glow of distant worlds guiding your thoughts into slower orbits. If these gentle journeys help you rest, a quiet like and soft subscribe helps others find their way here too. For now, breathe easy and let the unanswered questions hold you far above the sleeping world. Beyond the thin shimmer of our atmosphere, a golden mirror drifts in the dark. The James Webb Space Telescope hangs there in quiet patience, catching light so old that it began its journey when nothing like Earth yet existed. Each beam that settles onto its honeycomb of mirrors carries a story. And lately those stories have been strange enough to keep even the calmest scientists wide awake. They thought they knew the outline of the universe's childhood. Galaxies, in that picture, were meant to start small and clumsy, taking billions of years to grow large and graceful. Black holes would swell slowly. Step by step, everything would obey a long, careful timeline. But the light James Webb sends back keeps hinting that the cosmos may have moved faster, or taken hidden paths no one had seen before. When the telescope looks toward the cosmic dawn, it is peering into a universe only a few 100 million years old, just a tiny fraction of its present age. At that point, astronomers expected to find faint, fragile galaxies, like scattered sparks trying to catch the early cosmos. In their models was a place of beginnings, not of finished structures. Instead, the images arrive and show something else. In that young light are enormous galaxies, already blazing with billions of mature stars. Some appear to hold more mass than our own Milky Way, even though the universe itself was still a child. They carry the poise of age in a sky that should have been too young to hold them. It is as if you visited a field you planted yesterday and found a full-grown oak tree standing there, rings hidden deep in its trunk, whispering of years that have not yet passed. For a long time, the standard story was gentle and orderly. Tiny seed galaxies formed first. Clouds of gas and dark matter, they merged, collided, pulled at each other, and slowly grew. Stars kindled inside them, lived, died, and scattered heavier elements into space. Over billions of years, the great spirals and massive clusters we know today gradually took shape. The galaxies James Webb is revealing seem to have skipped much of that patient process. They look as though they rushed ahead, appearing almost fully formed while the universe was still wiping early light from its eyes. In quiet offices, researchers scroll through the data, their screens glowing softly in the dark. Many describe the feeling the same way they went looking for cosmic infants and instead met giants. The light from these distant systems carries the fingerprints of heavy elements such as carbon and oxygen, material that is usually built up slowly over many generations of stars. Yet somehow, in these young epochs, those signatures are already there, as if the universe has sped through several rounds of stellar life and death in the space of a single breath. What makes it harder to ignore is the sheer number of these objects. If James Webb had found only one oversized galaxy in the early universe, it might have been seen as a rare oddity. Instead, the telescope keeps finding more of them, scattered across the deep sky like bright islands. There are dozens already, and likely many more, just beyond the reach of current surveys. Together, they suggest that the early cosmos may have been crowded with giants, not sparsely dotted with tiny, struggling structures. Faced with this, astronomers begin to loosen their grip on old assumptions. Perhaps dark matter gathered itself more efficiently in those early times, pulling ordinary matter inward far faster than it does now. Perhaps gravity behaved a little differently under the extreme conditions that existed shortly after the beginning, drawing things together on large scales with unexpected strength. Or perhaps we are simply missing entire chapters of the universe's story, brief but powerful episodes of creation that left behind only faint traces in the light we see today. Some ideas are bolder still. One suggestion is that these huge galaxies formed around primordial black holes, dense seeds that came directly from the universe's first moments, instead of from collapsing stars. Their intense gravity would have given matter a head start, letting galaxies gather quickly, like storms forming around invisible centers. If that is true, then the early cosmos may have used tools that are no longer active now. Scaffolding taken down once the main structure was in place. The light from these galaxies makes the puzzle sharper. It arrives at wavelengths that usually belong to older, more chemically enriched systems, as if they have already gone through cycles of star birth and star death that should have taken much longer. It is like finding finely minted coins deep in a mine long before anyone has learned how to shape metal. The laws of physics are still intact, but the order in which things happened may not be what we thought. Under that weight, it is natural to wonder whether the universe passed through hidden phases we have never truly seen. Times when time itself flowed differently, or when gravity's hand was a little heavier. It is also possible that our equations are mostly right, but missing one quiet, important term that would make all of these impossible giants fit neatly into place. Until that missing piece is found, the galaxies linger in the mind like unanswered questions. And if galaxies could grow so quickly, then the black holes at their centers may have done the same. Supermassive black holes, millions or billions of times more massive than our sun, are usually thought to be slow creations, built over long ages as smaller black holes merge and as gas and dust spiral inward. Yet James Webb seems to be catching hints that some of these monsters were already in place when the universe was very young, as if they, too, have taken a faster path than expected. While those mysteries simmer, the telescope turns its golden eye toward another puzzle: stars that are being born in places where no stars should survive. In the heart of the Crab Nebula, thousands of light years from Earth, lies the wreckage of a star that once died in a bright supernova. The cloud of gas and dust it left behind is turbulent and harsh, flooded with radiation and shock waves. By the old rules, such a place is too violent for new stars to form. To make a star in the familiar way, you need calm and cold, dense clouds, temperatures hundreds of degrees below zero on the Fahrenheit scale, and millions of years for gravity to gently squeeze the gas together until nuclear fusion flickers to life. James Webb is now watching that quiet recipe being ignored in regions that should behave like furnaces. With temperatures soaring to millions of degrees and fierce radiation sweeping through space, The telescope sees the soft glow of new stars beginning to gather. It is like watching delicate flowers take root and bloom inside the heart of a blast. Petals opening in a wind meant to tear them apart. Winds from nearby massive stars race through these regions. Streams of particles strong enough to scatter gas clouds before they can collapse. And yet, Webb's images show small, dense knots of light, young stars, or stars almost ready to ignite, holding themselves together. They are forming in defiance of the very conditions that should unmake them. Even more surprising is the speed of their birth, where ordinary star formation takes millions of years. These strange stellar rebels seem to complete their transformation from cloud to shining star in only thousands of years, on cosmic timescales that is almost instant, like watching a life begin and finish between two steady heartbeats. They appear to skip entire stages of the tidy diagrams drawn in textbooks, leaping straight from drifting gas to fully burning star, as if someone had quietly pressed fast forward. In the Orion Nebula, another well-known cradle of stars, James Webb finds more rule-breaking. Young stars there are forming in gravitational fields so tangled and strong that they should be torn apart before they can settle. Nearby, heavyweights tug at them from many directions, creating tides that stretch and pull like a cosmic rack. Even so, these fragile stellar seeds survive. They grow. They begin to shine. Somehow, in all that chaos, they find a way to stay whole. Dr. Michael Chen and his colleagues at Harvard have been studying the light from some of these unusual stars. What they find inside them deepens the sense of strangeness. Their atmospheres hold heavy elements that should require many cycles of star birth and star death to create. Yet these stars, measured on the scale of the universe, have only just appeared. It is like opening a brand new book and finding the pages already worn, the margins crowded with notes from readings that never happened. Their brightness adds another twist. Some stars that seem to have masses similar to our sun are radiating with the power we would expect from stars many dozens of times heavier. According to the usual rules, such small stars should not be able to burn so fiercely. The reliable relationship between a star's mass and its luminosity, a pattern astronomers have trusted for generations, seems to bend in their presence. It is as if these stars have discovered fusion pathways our equations say they should not be able to use, turning modest amounts of mass into floods of energy. That does not mean we must throw away everything we know, but it does suggest that our picture of how stars live and shine is missing some subtle, important details. What gestures towards something larger is how often these unlikely stars appear. Webb's ongoing observations keep revealing new examples, scattered through different regions of space. They no longer look like rare curiosities. Instead, they begin to resemble a quiet but persistent pattern, a sign that the universe has more than one way to light a star. As the data slowly accumulates, astronomers notice a soft trend emerging. This strange, accelerated star formation is not limited to a single famous nebula or one unusual patch of sky. Hints of it begin to show up in other places that once seemed calm and ordinary, in clouds and regions long thought to be uneventful. The phenomenon appears to be reaching into parts of the cosmos that, until now, were considered steady, predictable, and gently, previously stable. In the soft hush of the cosmos, where gravity and light weave stories older than memory, new possibilities begin to shimmer at the edges of what we think we know. Some scientists whisper that these unusual stars, those swift, unruly beings forming where they should not, might be guided by dark matter, that quiet and unseen companion that shapes galaxies without ever letting itself be touched. Perhaps, in its invisible currents, it cradles gas clouds in ways we cannot observe, smoothing their collapse, coaxing them into starhood faster than gravity alone could manage. Others imagine something different, something gentler, that the universe itself has drifted into a new chapter, a phase in which the conditions of space have settled just right to trigger a fresh style of stellar birth. Maybe, in this epoch, the cosmos carries a subtle warmth or rhythm that allows stars to take shortcuts. There is even a thought more daring, more delicate, that quantum effects might be widening their reach, letting matter slip through barriers that once seemed firm, tunneling into configurations that gravity would otherwise forbid. Despite how fantastical these ideas sound, the stars themselves do not appear chaotic. They gather in clusters, not as noisy randomness, but with a quiet intentionality. Some are separated by distances so large that light itself needs years to cross them. Yet their births seem to echo each other. When astronomers map their positions and motions, faint patterns appear almost like constellations, hidden within the fabric of space-time. A few theorists wonder aloud whether gravitational waves might be carrying subtle messages across the void, rippling gently through the dark and nudging star nurseries into harmony. Formation events unfold as if tuned to the same invisible rhythm, synchronized across distances no ordinary signal could cross in time. If stars can bend the rules this way, it is natural to wonder about the worlds that circle them. Around 50 light-years from Earth, orbiting a star called TOI 715, lies a planet that seems to exhale in a way no known chemistry can explain. When the James Webb Space Telescope studied the starlight filtering through this world's sky, the results settled like a quiet shock in the minds of the researchers watching. There appears to be far more oxygen than our own Earth holds. Thick bands of nitrogen stacked in proportions that should quickly break apart, and delicate traces of water vapor resting in layers that, by all common models, should collapse under their own weight. It is like finding a creature breathing underwater despite having no gills, something living as though the rules of its environment had been rewritten around it. According to traditional models, this planet ought to be bare stone. It sits too close to its star for stable oceans or drifting clouds. Any liquid water should have evaporated long ago, leaving behind a landscape charred and still. Yet the telescope detects immense cloud systems stretching like soft blankets across the surface, reshaping themselves in wide, slow arcs. The pressure in its atmosphere is roughly 3 times that of Earth's, heavy enough to flatten oceans. And yet, instead of crushing everything beneath it, the pressure seems to carve astonishingly gentle weather, broad circulations that look almost welcoming. Then the data revealed something even more troubling. Webb's instruments detected traces of compounds that, on Earth, come almost exclusively from industry chemical signatures that, here at home, require machines, fire, electricity, and intention. But this distant world, by every measurable clue, shows no recognizable form of technology, no patterns of light or heat that would point to civilizations shaping its air. The chemicals simply exist, as though produced by an unseen process with no natural origin we can name. Dr. Sarah Kim, who has been studying these strange exoplanet atmospheres for years, has noticed a pattern spreading across her research. She estimates that nearly 1/3 of rocky planets, examined closely by Webb, hold atmospheres that refuse to follow ordinary chemistry. Elements appear in combinations that should rapidly react away, yet they linger calmly, suspended as if held in balance by some quiet force. Energy seems to be flowing through these skies without matching any familiar source. Neither starlight, nor volcanic heat, nor radioactive decay can account for the sustained patterns. One of the most astonishing examples is the world identified as HD 4037G, a cold string of symbols that hardly reflects the strangeness beneath it. Its atmosphere contains metallic hydrogen drifting freely as a gas, even though such hydrogen should condense into liquid under those measured conditions. More than that, the hydrogen seems to arrange itself into delicate structures, complex, crystalline forms that are somehow still airy and diffuse. It is like watching patterns freeze into shape without ever turning solid. The movement of this atmosphere is stranger still. Instead of swirling randomly the way winds do here at home, its layers surge across the planet like tides in a vast sky ocean. Whole sections of the atmosphere migrate from dayside to nightside in a steady rhythm, their paths forming sequences that look more mathematical than meteorological. Storms bloom and do not fade. They burn for years, casting lightning bright enough to be detected from unimaginable distances. Inside them, glowing knots of plasma gather into simple geometric shapes, persist far longer than turbulence should allow, and drift like lanterns carried by an unseen hand. The chemistry of these worlds deepens the mystery. Heavy elements, those that usually form only in the violent hearts of stars, appear in clean, unweathered abundance, as if manufactured carefully rather than scattered by supernova winds. And the isotopes, the slightly heavier or lighter siblings of ordinary atoms, appear in ratios that do not match any known pathway. They line up almost neatly, like numbers chosen rather than inherited. Then there is the synchronization. On planets separated by dozens of light years, atmospheric changes unfold in unison. When oxygen levels shift on one world, a similar rise or fall occurs on another, far too distant to be influenced by light-speed signals. Hours pass, and skies on multiple planets change together, as though listening to the same silent conductor. No natural mechanism we know can coordinate atmospheres across such distances so quickly, and yet the pattern holds, delicate and uncanny. In some cases, molecular networks within these atmospheres begin to behave in ways that edge toward life. Chains of compounds make copies of themselves, growing more intricate, shaping the airflow around them in ways that seem to help them survive. These formations shift pressures and temperatures, making their host atmospheres more layered and more stable, as though carrying out slow-motion terraforming. They evolve not through genetics, but through structure, through chemistry learning to echo its own shape. The thought is staggering. Either our understanding of atmospheric physics is missing something vast and foundational, or these worlds are being altered by intelligences that remain hidden from our view. Quiet hands may be rearranging their skies, or perhaps the atmospheres themselves are becoming something like organisms planet-spanning, ancient and airy. Yet even these mysteries feel small compared to what lies deeper, where gravity thickens and time begins to fold. At the heart of a distant galaxy catalogued as GN11, some 11 billion light-years from Earth, rests a black hole so massive that its very existence seems like a contradiction. It is thought to hold the weight of roughly 40 million suns, and the light around it suggests it reached this size when the universe was only about 400 million years old, far too young for such a giant to have grown by the familiar. Slow steps. Einstein's equations describe a limit, the Eddington limit, a speed at which black holes can swallow matter before the resulting light pushes the rest away. Even if a black hole fed constantly at that maximum rate, it would need billions of years to reach the mass we now observe. But this ancient object seems to have grown in a fraction of that time, as if the cosmos briefly lifted the speed limit and allowed it to surge forward unchecked. And this is not an isolated case. Webb has found many such black holes scattered across the early universe, each one violating the usual rules as though those rules simply had not yet been written. They seem to have skipped the slow accretion process, swallowing stars and gas clouds in enormous gulps that should have blasted away incoming material with their own radiation. Instead, they kept feeding, growing rapidly, reshaping their galaxies in the process. Dr. James Wright, who has spent years tracing the growth of black holes across cosmic time, calculates that some of these giants must have consumed matter at rates far beyond what the Eddington limit should allow. At those speeds, the surrounding glow should have pushed material away, starving the black hole almost immediately. But reality seems to disagree, and the way these black holes shape their galaxies is equally startling. Instead of guiding star formation slowly over eons, they appear to sculpt entire structures quickly, as if their gravity pulls the galaxy into place around them. Systems that should take billions of years to reach their familiar shapes appear instead already complete, their arms and cores arranged neatly around a central darkness. Even more puzzling are the energy signals rising from their surroundings. Gravitational waves seem to arrive slightly before the corresponding light, almost as though space-time is being bent in a way that lets one message slip through early. Near these black holes, time itself feels distorted. Stars move along their orbits faster than the predictions drawn from relativistic calculations would suggest, as though the flow of moments around them has shifted into a rhythm we do not yet fully understand. Out in the deep quiet, far beyond the familiar rivers of stars, James Webb has noticed something about the largest black holes that feels almost like a secret being passed from one giant to another. These supermassive hearts of darkness do not simply flicker on their own. When astronomers watch their brightness and activity over long stretches of time, a strange pattern begins to emerge. A black hole in one distant galaxy changes its rhythm, its fierce glow rising or softening. And then, across an unimaginably large gulf of space, another black hole seems to echo the same change. If these shifts are truly linked, and not just coincidence, the timing is deeply unsettling. The responses appear to happen too quickly for any signal traveling at the speed of light to carry the news from one to the other. It is as if these black holes are somehow connected, forming a quiet network spread across the cosmos, adjusting themselves in concert through channels we do not understand, bending the usual rules of space and time in ways our equations do not yet describe. The mystery deepens when scientists examine the X-ray glow pouring out from the swirls of matter around these objects. That light does not look like anything produced by the familiar dances of hot gas, magnetic fields, and shock waves. Instead, the energy patterns follow curves that refuse to fit any known astrophysical process. It is as though the black holes are reaching into a deeper reservoir of power, drawing on sources beyond the simple conversion of mass into energy that Einstein's famous equation describes. Something unseen seems to be feeding them. Some fundamental aspect of reality that has not yet been given a name, looking for ways to make sense of this. Some researchers suggest that at least a few of these black holes may have formed directly from the first moments after the Big Bang, primordial knots of gravity that collapsed before any stars existed at all. In that picture, they skipped the usual path, never passing through the life and death of ordinary suns. Others entertain an even stranger idea. Whispered carefully in late-night conversations, perhaps these black holes are not just dense objects, but openings into regions where the laws of physics themselves are different. Gateways into neighboring domains where the constants of nature take on new values. For cosmologists, the implications are both thrilling and unnerving. If these black holes can ignore the limits that we have treated as fundamental, then our understanding of gravity, space-time, and causality may be only a close approximation, a local version of a much more complex truth. The rules we know might be like the shallow ripples on the surface of a deeper sea. And still, the story does not end there. When Webb's instruments gently spread the light from certain ancient galaxies into rainbows for analysis, they reveal something startling hidden in those colors. In a galaxy sometimes catalogued with a dry, almost forgettable name, MAX, 149 astronomers find chemical fingerprints that should not belong to such an early time. This galaxy shone when the universe was only about 500 million years old. A moment when the cosmic story should have been very simple, yet, in its light, scientists see the telltale marks of heavy elements: gold, platinum, uranium, and others that usually take long ages to accumulate. These elements are not made in calm, steady processes. They are forged in the most violent events the universe has to offer, the explosive deaths of massive stars, and the fierce collisions of neutron stars spiraling together and tearing themselves apart. Each such event contributes only a little to the cosmic stockpile. Over billions of years, as stars are born, live, and die, galaxies slowly grow richer in these heavy elements. To find them already present in generous amounts when the universe was so young is like entering a time when people still drew simple figures on cave walls and discovering an entire library of bound and finished plays on a shelf. In her work at a cosmic chemistry laboratory, Dr. Lisa Martinez has been tracing these strange fingerprints across many early galaxies. The more she looks, the less these anomalies seem like rare exceptions. Nearly half of the oldest galaxies in her surveys appear to be filled with heavy elements that, according to our current understanding, should not exist in such abundance for many billions of years. In some, there are clear signs of elements that usually require neutron star collisions, even though there has hardly been enough time for massive stars to form, evolve into neutron stars, and then collide. When she and her colleagues examine the isotopes, the slightly heavier and lighter versions of each element, the puzzle becomes more complex. On Earth and in nearby stars, the ratios of isotopes follow patterns that reflect their origins, each one a quiet signature of the nuclear processes that created it. In these ancient galaxies, the ratios do not match any known path. It is as if the elements had been put together in ways that bypass the usual sequence of stellar furnaces and explosions, assembled through methods that have never been seen in our own corner of the cosmos. In a massive galaxy cluster known as Abell 2744, Webb's data reveals something even more unsettling. The light from some of its ancient galaxies carries the signature of technetium, an element so unstable that it disappears completely over spans of time measured in only a few million years. Yet these galaxies are billions of years old. For technetium to be present now, it must be created again and again through some ongoing process, or else our understanding of how radioactive decay works must be missing a small but crucial piece. Alongside technetium, these galaxies show rare Earth elements in concentrations thousands of times higher than any model predicts. Under ordinary circumstances, such elements form in tiny quantities, the delicate side effects of complex stellar reactions. Here, they appear as though mass-produced, gathered into their galaxies through mechanisms that leave no obvious traces in the surrounding light. Some of the spectra even hint at super-heavy elements with atomic numbers beyond anything printed in our periodic tables, elements that theory says should fall apart almost instantly, yet whose signatures seem to persist calmly over cosmic time. Perhaps most haunting is the way these elements are distributed. Instead of the messy, scattered patterns expected from repeated explosions and random mixing, the abundances in some galaxies appear to follow clear mathematical relationships. Ratios line up in neat progressions, like steps in a geometric sequence. It looks less like the aftermath of chaos and more like a recipe carefully followed. In a few cases, the data suggests that matter has been quietly transformed from one element into another, without producing the usual byproducts of nuclear reactions, as though some gentle hand has been turning the knobs of the atomic world directly. Faced with this, scientists are forced to stretch their imaginations. Perhaps, they think, the early universe was able to access states of matter that no longer exist today. Exotic forms that could rapidly synthesize heavy elements through quantum tunneling and other subtle effects. Maybe there were fleeting interactions with parallel realms where nuclear reactions unfold differently, spilling their products into our own space like color leaking from one page to the next. Or perhaps these galaxies were seeded, intentionally or otherwise, by processes that have left no trace beyond the elements themselves. As strange as all this is, the story becomes even more delicate when Webb turns its gaze to the oldest light it can see, around 13 billion light-years away, at the very edge of its reach. The telescope gathers faint photons that have been traveling almost since the universe began. These tiny particles of light set out when the cosmos was roughly 100 million years old, during the early and mysterious epoch when the first stars are thought to have ignited. According to the standard picture of Big Bang nucleosynthesis, that newborn universe contained almost nothing but hydrogen and helium, with only the slightest dusting of lithium. The first stars, in that view, should have been massive and simple, burning nearly pure hydrogen in straightforward nuclear reactions. Their light ought to reflect that simplicity. But when astronomers spread this ancient light into spectra, what they see does not align with the simple story. Instead of just the clean lines of hydrogen and helium, they find absorption features that correspond to molecular structures far more complex than anything that should exist in such a young, chemically plain cosmos. Mixed into the ancient light are faint signatures of complex organic molecules, heavier metals, and compounds that ordinarily require extended chains of reactions and stable environments to form. For Dr. Robert Kim at the Early Universe Research Center, reading these spectra feels like sifting through layers of cosmic dust and finding artifacts that do not belong to that age. It is a kind of cosmic archaeology, uncovering traces of sophistication in a time that models say should have been primitive and raw. The light suggests that these first stars might not have lived alone as simple, blazing spheres. Instead, they may already have been accompanied by planetary systems, with chemical cycles quietly running in their skies and on their surfaces at a time when the universe was supposed to be too young for such complexity. The way this ancient light is polarized adds another delicate thread. Light waves can vibrate in different orientations, and those orientations carry clues about what the photons have passed through. The primordial light Webb observes shows polarization patterns that imply it moved through structures more ordered than the simple, smooth gas expected in the early universe. It is as if the photons had wound their way around invisible frameworks, hints of shapes and patterns in places we once imagined as nearly empty. The behavior of the first stars, as inferred from this light, is equally surprising, rather than burning in the chaotic, uneven way expected of primitive stellar furnaces. They seem to have shone with remarkable steadiness. Their brightness appears carefully regulated, staying nearly constant for millions of years instead of jittering and flaring the way most stars do. Such stability suggests that something, whether internal physics or external conditions, was gently guiding their output, keeping their luminosity in a narrow, precise band. Even more quietly astonishing is the mix of elements these stars appear to have produced, instead of generating a broad, somewhat random spread of elements. Their output seems tuned toward the specific ratios needed to build Earth-like planets, the right balance of light and heavy components to form rocky crusts, metallic cores, and complex atmospheres. It is as though, very early on, the universe was already preparing the raw materials for worlds that could one day host weather, oceans, and perhaps even life. The photons themselves remember the clouds they touched along their journey. Every time they were absorbed and re-emitted by a primordial gas cloud, they picked up subtle traces of the molecules they encountered. When astronomers decode those traces, they do not find only the simple ingredients of a sterile universe. Instead, they uncover spectral hints that complex organic chemistry was already operating when the cosmos was supposedly sterile and lifeless. Most mysteriously of all, that ancient starlight does not arrive as a steady, featureless glow. When astronomers study it carefully, it seems to breathe. The light brightens and softens in delicate cycles, and those cycles repeat with a precision that feels almost musical. The variations are not random twinkles or the rough beating of unstable stars. They follow patterns, rising and falling in intervals that line up with simple mathematical relationships, as if the earliest suns were somehow keeping time with one another across unimaginable distances. Some of the spectral features, the tiny dips and marks in the light, appear to arrange themselves into sequences that look eerily like code. When translated into simple on and off patterns, bright and dim, present and absent, they resemble the binary rhythms used in digital communication. These sequences match no known astrophysical process, no pulsation pattern, no rotation, no known type of starquake. Yet they carry hallmarks of something engineered, something that repeats with intention rather than accident. It is as if those first stars were not only shining, but speaking, their light carrying messages quietly across the young cosmos. The thought that follows is difficult to hold without a small shiver. Either the first stars were born through mechanisms entirely unlike anything we see today, carrying built-in rhythms that our models never predicted, or the universe began with a level of structure far beyond the soft, simple fog of hydrogen and helium we once imagined. The ancient light suggests that intelligence, whatever that word might mean on cosmic scales, could have emerged far earlier than anyone thought possible. Perhaps even before the first galaxies had fully gathered themselves into shape. And still, in Webb's gaze, the universe continues to misbehave in other ways. At a distance of roughly 4 billion light-years from Earth, two massive galaxies drift toward each other in a slow-motion embrace. According to everything we know, galactic mergers are long, drawn-out affairs. Gravity pulls and tugs, and over hundreds of millions of years, stars and gas clouds are rearranged, flung outward, or drawn inward to shape a new, larger system. Astronomers have simulated these dances countless times, guided by Newton's laws and Einstein's relativity, and the results have always agreed well with the collisions we could observe. Yet the images Webb now sends back show some mergers unfolding with startling speed, like a time-lapse played too fast. The pair known as the antennae galaxies offers one of the most unsettling examples. These two spiral systems, with their long tidal tails reaching out like delicate insect feelers, should be in the early stages of a merger expected to take billions of years. Instead, Webb's observations suggest that they are completing gravitational moves that should require eons, finishing in mere millions of years processes that our models insist should unfold 1,000 times more slowly. The stars and gas seem to reorganize themselves, almost as if the galaxies had agreed on the outcome in advance. Dr. Patricia Chen at the Galactic Dynamics Institute has been studying these impossible collisions with quiet intensity. Her team's analysis suggests that, as the galaxies interact, they somehow share mass and energy in ways that seem to bypass the slow mediation of gravity. When one galaxy loses stellar material, the other gains the same amount almost instantly, as though some hidden connection links them beyond the finite speed of light. The exchange looks too neat, too precisely balanced, to be the work of simple, chaotic tidal forces. In simulations based purely on known physics, colliding galaxies scatter their stars in messy, intricate patterns. Yet Webb's images reveal mergers where the resulting structures show uncanny symmetry, with arcs and streams of stars settling into beautifully ordered shapes. It is almost like watching a choreographed performance on a stage so vast that each dancer is a sun. And still the pattern holds. The strangeness deepens when scientists study the energy these collisions release. The gravitational waves that ripple out from the merging systems arrive with frequencies suggesting that something more than ordinary three-dimensional space is involved. It is as if the galaxies are briefly dipping into additional spatial dimensions during their encounter, using extra directions to rearrange their mass more efficiently. In the debris that is flung outward, the usual rules of momentum seem to bend. Streams of stars and gas follow paths that curve back on themselves, forming loops and spirals that should not be stable under normal gravity. Even more unsettling, some of the light from these debris streams appears to arrive before the collision events that created them. Like echoes arriving before the sound, it is as though, in those turbulent regions, the normal order of cause and effect has been softened, allowing information, or perhaps the paths of particles themselves, to fold through time and quiet. Forbidden arcs across the sky, Webb has now watched multiple galaxy pairs, separated by billions of light years, going through remarkably similar mergers at nearly the same cosmic moment. Their tidal tails, their bridges of stars, their central coalescences all follow matching patterns, unfolding within overlapping time windows. From our vantage point, it looks as though the collisions are synchronized, as if scattered galaxies are responding to a shared script that spans distances. Light would need many lifetimes of the universe to cross. From these strange unions, new galactic forms emerge, hybrid systems whose mass distributions and orbits defy the neat expectations of orbital mechanics. They hold shapes that, under ordinary gravity, should quickly collapse or shear apart. To remain stable, they would need a constant supply of energy, a steady push against the tug of their own mass. Yet there is no clear sign of the necessary engines, no blazing quasars, no vast jets, no obvious sources to keep them balanced, and still they endure. In some of the most curious regions, the space around these mergers seems to warp more sharply than Einstein's equations predict. Light passing through these zones bends into curves steeper than expected, as if sprinkled through with exotic forms of matter or governed by a version of gravity slightly stronger than the one we know. The distortions are local, like pockets where the rules have been quietly adjusted. The selectiveness of the destruction and survival is perhaps the most haunting detail. Within the chaos of colliding galaxies, whole planetary systems are torn from their stars or swallowed into central maelstroms, but not in the purely random way models would suggest. Certain kinds of systems seem to be preserved with suspicious consistency. Worlds with particular masses, orbital distances, or chemical makeup slip through the upheaval relatively untouched, while others are more often ejected or destroyed. It is almost as if the collisions themselves are sorting the contents of the galaxies, keeping what meets some invisible criteria and discarding the rest. Taken together, these impossible mergers hint that the large-scale structures of the universe may be playing by rules we have not yet uncovered, shaped by forces or principles that move beyond the familiar language of gravity alone. And then Webb turns from these vast, luminous collisions to something far lonelier: worlds with no suns at all, out in the dark spaces between the stars, where starlight thins into almost nothing. The telescope has begun to find planets drifting alone. These solitary bodies, separated from the glow of any parent star by trillions of miles, move quietly through the interstellar night like ghosts. Conventional wisdom says such rogue planets are the exiles of planetary systems, worlds flung out by gravitational scuffles during their formation, doomed to wander forever in freezing darkness without the warmth of a nearby sun. They should quickly cool, their surfaces sinking toward temperatures barely above absolute zero, their skies still and dead. But Webb's observations paint a different, uncanny picture. Some of these orphan worlds are not dark at all. They shine faintly in infrared, the soft glow of their own warmth giving them away. The planet cataloged as WISE 830 plus 2,837 is one of the most startling examples, floating roughly 40 light-years from Earth. With no star in close attendance, it radiates energy more like a small, quiet sun than a frozen rock. Its estimated surface temperature reaches nearly 1,000 degrees Fahrenheit, warm enough to keep entire oceans in liquid form if water is present, oceans that, by all conventional expectations, should have frozen solid countless ages ago. Dr. Alexandra Rodriguez from the Planetary Sciences Division has been following these wanderers with a patient, focused curiosity. Her surveys suggest that such rogue planets are not rare curiosities but common citizens of the galaxy. There may be billions of them drifting through the Milky Way alone. Some pass near star systems. Some roam the deep voids between spiral arms. And yet many of them show signs of being anything but inert. Data from Webb indicates that a surprising number of these worlds have active weather systems. Their atmospheres seem to circulate, with winds and currents transporting heat from one side to another. Subtle variations over time reveal patterns that resemble seasons, periodic shifts in temperature, cloud cover, and circulation, all unfolding despite the lack of a sun to drive those cycles. Instead of the chemically quiet, frozen gases expected from planets locked in perpetual night, their atmospheres show complex chemical networks, as though reactions are being continually stirred by hidden energy sources. On some of these rogue worlds, Webb detects oxygen mixed with other reactive gases in proportions that, on Earth, would suggest ongoing processes akin to photosynthesis, the gentle work of life collecting light and turning it into energy. But in the darkness between stars, there is almost no light to harvest. These signals hint at cycles we do not yet understand, chemistry that appears to be maintained, renewed, and balanced without the steady hand of a nearby sun. The more carefully astronomers look, the more their attention is drawn to something that, in a quiet way, might be the most unsettling clue of all. These lonely planets, drifting in the black between the stars, seem to be wrapped in magnetic fields far stronger and more structured than expected. The most unsettling discovery involves magnetic field measurements. Out in the deep dark between the stars, where no sunrise ever comes, Webb has found that some of these wandering worlds are wrapped in invisible power. These isolated planets, drifting without the warmth of a sun, somehow generate magnetic fields stronger than the one that shields Earth. Even though they seem to lack the churning, molten metal cores that usually act as planetary dynamos, their magnetism should be weak or nearly absent. Yet the patterns Webb infers from their emissions show strong, structured fields, as if these worlds are quietly reaching into an energy source we do not yet know how to name. The shapes of those fields are just as strange. Instead of being simple, like a bar magnet or a slightly lopsided version of Earth's dipole, they twist into intricate configurations that shift and realign with calm, deliberate grace. It is as though invisible lines are being braided and unbraided around the planets, guided by rules that have nothing to do with molten iron or slow geological motion. Even more quietly unsettling is how some of these rogue planets behave in groups. Webb has watched clusters of orphaned worlds traveling together, maintaining precise distances from one another as they move through the galaxy. They are not bound to any star, yet they drift in formation, keeping geometric arrangements as stable as if connected by unseen threads. Triangles, arcs, and long, evenly spaced chains of planets glide through space, holding their shapes over time in a way that random gravitational nudges should quickly disrupt. They move less like debris and more like a fleet. From a few of these lonely wanderers, faint radio whispers reach Webb's instruments. The signals are not the broad, noisy emissions expected from natural magnetic storms or simple cosmic processes. Instead, they show crisp modulations, rises and falls in intensity. Shifts in frequency that do not match any known natural source. When plotted and studied, the patterns resemble engineered communication systems, structured bursts, repeating intervals, and embedded sub-patterns that feel suspiciously like encoding. The broadcasts seem to favor certain directions, aimed toward particular patches of sky, and their timing suggests something more than idle noise, as if these planets are sending quiet messages into the dark. In the soft glow of infrared, some rogue worlds reveal surface features that look uncannily like deliberate designs. On their night sides, where only their own warmth outlines the land, large-scale patterns appear, long straight lines that stretch for thousands of miles. Circles nested inside larger circles, and grids that span entire continents. These shapes show a mathematical precision that geology does not ordinarily produce. They do not resemble the ragged cracks of tectonic plates or the soft curves of erosion. Instead, they look like blueprints traced on a planetary scale, drawn in heat rather than ink. When Webb studies the thermal emissions from these wandering planets, another oddity emerges. Instead of slowly cooling over billions of years after being flung away from their home stars, many of them maintain steady, elevated temperatures. Their warmth does not fade as simple physics says it should. There are no visible suns nearby, no obvious tidal interactions with massive companions, and yet their interiors seem to be powered by some continuous process. The heat profiles are smooth and stable, more like the output of a controlled engine than the leftover glow of ancient formation. Most mysterious of all, some of these rogue planets do not drift in the aimless paths expected of exiles. Their trajectories bend and curve in ways that require constant, gentle adjustments. As if they are following invisible waypoints, they turn toward specific regions of space, alter course in subtle arcs, and occasionally adjust their speed in ways that make their motion look more like travel than wandering. To follow such paths without the guiding pull of a star would require some form of navigation, some persistent force or control that we have not yet confirmed. It leaves open the possibility, whispered more than stated, that entire planetary bodies might be moving under guidance, or responding to a map written on scales we do not yet perceive. All of this hints that a planet does not need a star to be complex, warm, or even organized. Worlds may thrive in the deep night, lit from within, following principles that stretch far beyond the simple textbook picture of a planet bound to its sun. And yet, even these drifting enigmas are only part of what Webb has uncovered about water hiding in places it should never be. Deep within the Orion Nebula, about 1,500 light-years from Earth, lies a bright, turbulent nursery where stars are being born from clouds of gas and dust. The temperatures in some of these regions reach thousands of degrees on the Fahrenheit scale, and harsh ultraviolet radiation floods the space between newborn stars. In such an environment, delicate molecules do not last. Water, in particular, should be torn apart almost as soon as it forms, its bonds snapped by energetic photons, its atoms scattered by violent winds. But Webb's instruments see something else. In the very heart of this hostile region, vast clouds of water vapor drift through space, spanning distances measured in light years. Their spectral signatures remain stable over time, suggesting that the water molecules are not simply flickering into existence and then vanishing. Instead, they hold together, maintaining their structure where every rule of chemistry says they should be destroyed in moments. It is like hearing a fragile melody being played clearly in the middle of a storm. At the Astrochemistry Research Institute, Dr. Maria Santos has been painstakingly charting these impossible reservoirs. Her analyses show water concentrations that not only exist, but flourish densities in some spots approaching those of Earth's tropical air. Yet hanging in the near vacuum of interstellar space, there are no oceans, no clouds hugging a planet's curve, just free-floating water vapor in sheer abundance, held aloft in nothing. When she looks at the isotopes within that water, the particular flavors of hydrogen and oxygen that make up each molecule, the story becomes even stranger. On Earth, in stars, and in most interstellar clouds, the ratios of isotopes follow patterns set by well-understood nuclear and chemical processes. In the Orion water clouds, those ratios are skewed into unfamiliar alignments. They suggest that the water did not form in the usual ways, through ordinary stellar reactions or gentle chemical combinations in cool regions. Instead, it hints at exotic nuclear pathways, processes that might twist atoms together under conditions we have never recreated, guided by rules that verge beyond the edge of our physics. Even the way this space-borne water moves resists explanation. Rather than dispersing evenly, thinning out and fading as time passes, the vapor gathers itself into intricate structures. Webb's images and spectra suggest the presence of filaments, shells, and rounded clumps that hold their shapes over spans of time measured in millions of years. Some of these formations, when mapped, resemble enlarged versions of cellular structures, nested layers, internal cavities, and boundary-like surfaces that look oddly reminiscent of membranes. The water does not simply sit in place. Either it flows. Currents sweep through the nebula, carrying moisture along paths that span dozens of light years. There are rising and sinking motions, large loops, and circulating flows that resemble weather systems, but on a scale far beyond any planetary atmosphere. There are no solid surfaces here, no oceans or continents to guide the motion, and yet patterns emerge and repeat, as though the water itself has learned to cycle and renew without the usual drivers of wind and heat gradients. These interstellar water cycles appear surprisingly self-sustaining. Molecules break apart and reform, but the overall reservoirs persist. The energy required to keep such complex motion and chemistry going is not obvious. There are no centralized engines, no neat sources to point to, yet the water keeps moving, reshaping, and maintaining itself. Most disquieting of all is the sense that these clouds are spreading. Over time, Webb has begun to see new regions that were once spectroscopically dry begin to show the telltale fingerprints of water. The rate at which these new clouds appear suggests formation processes far faster than any ordinary chemical pathway should allow. Atoms of hydrogen and oxygen seem to be organizing themselves into molecules with surprising speed, as though following some template or catalytic influence that is not yet visible. In some of these clouds, Webb detects faint hints of more complex chemistry mixed into the water traces of organic molecules, long carbon chains, and structures usually associated with living systems. These dissolved compounds drift in the middle of interstellar space, many thousands of light years from any known planet where life might have brewed. It is as though the ingredients of biology have been carried out into the open, stirred into vast cosmic seas that never touch a solid shore. The water itself sometimes appears to behave in ways that do not fit cleanly into the familiar categories of gas, liquid, and solid. In certain regions where temperatures and densities would normally boil or evaporate any condensed form, Webb's spectra hint at states where water seems to borrow properties from all three phases at once. It acts partly like a gas, spreading and flowing, partly like a liquid, forming coherent structures, and partly like a solid, maintaining internal order. These exotic phases remain stable under conditions that should destroy them quickly, suggesting that something deeper than standard thermodynamics may be at work. All of this pushes against the edges of chemistry as we understand it. Either water is far more resilient and adaptable than our experiments on Earth have led us to believe, able to survive and organize itself under extremes that once seemed utterly prohibitive. Or there are processes operating out there, perhaps rooted in quantum behavior or in forms of matter we do not yet classify, that are helping to assemble, protect, and sustain these cosmic reservoirs. It hints that the basic ingredients of life, especially water and organics, may be scattered and nurtured throughout the universe with a generosity we are only beginning to see. And still, as Webb continues to watch, it finds that even time itself can act strangely, bending and stretching near certain cosmic structures at the core of a galaxy often referred to as M87, lying about 54 million light-years away. A supermassive black hole sits like a dark lantern, its presence betrayed by the whirl of stars and gas around it. According to general relativity, such a massive object should warp space-time, slowing the flow of time for anything that ventures close. The effect is real but usually subtle, something we infer through careful measurements and precise clocks. What Webb is now watching near this black hole feels far from subtle. By tracking the positions and motions of stars in close orbit around the dark center, astronomers are seeing their paths and periods shift in ways that exceed Einstein's predictions by wide margins. Orbits that should remain nearly steady instead speed up and slow down on timescales of months. Not the long millennia that standard relativity would suggest. It is like staring at a clock in the sky whose hands lurch forward and then drag, not in response to any obvious cause, but as though time itself were being stretched and compressed in ripples. Dr. Stephen Park at the Relativistic Astrophysics Center has been following these anomalies with quiet fascination. His measurements indicate that the space around this massive object is not a smooth gradient of time dilation, as equations would expect. Instead, it seems to be divided into regions where time flows at different rates side by side. In some pockets, processes unfold faster than they should, while in neighboring volumes, everything lags, slowed beyond the predictions of classical relativity. These temporal gradients stand next to one another like invisible steps, abrupt changes in the pace of time across distances that should be far too small for such differences to exist. On paper, such a patchwork of time is not supposed to be possible. Yet Webb's observations hint that, in the vicinity of certain extreme objects, the universe may be weaving time into patterns as intricate as any lattice of stars, creating zones where seconds stretch and contract in ways that, for now, remain physically impossible to fully explain. As Webb continues to watch the cosmos with its quiet, patient eye, the story of time itself grows stranger. Near some of the most massive objects, the flow of moments does not bend smoothly, like a gentle curve, the way Einstein's equations would have us imagine. Instead, it seems to stutter and step. In certain regions, time dilation does not gradually increase or decrease. It jumps. Orbital periods change in sudden increments, as if time were climbing an invisible staircase rather than sliding along a ramp. Stars that circle close to heavy masses speed up and slow down in discrete shifts, not in the continuous way that relativity predicts. It is as though time is made of tiny, indivisible pieces, quantum steps, instead of an unbroken stream, hinting that beneath the soft fabric of space-time, there may be a deeper lattice, ticking in ways we have never seen before. These oddities do more than bend equations. In some stellar systems, cause and effect begin to blur. Webb has recorded light from distant explosions, arriving before the gravitational waves and other signals that should have caused them, as if the universe were showing us the flash before the strike. In a few cases, orbital changes appear months or even years before the disturbances that should have produced them. Paths twist and tighten. Then, only later, the triggering events unfold, like echoes, somehow preceding their sound. Most mysterious of all, these time distortions do not always stay local. When the strength of time dilation shifts around one massive object, similar changes sometimes appear around others many thousands of light years away. From our vantage point, they seem to respond together, as though the fabric of space-time is not a collection of separate wells and dents, but a connected web. Pull one strand, and another trembles far away. The influence of these temporal tricks runs down to the smallest scales astronomers can probe. In regions where time stretches or compresses most sharply, atoms themselves seem to age strangely. Spectra from stars deep inside these zones show energy levels and transition rates that do not quite match what our best atomic clocks would predict. Nuclear reactions appear to speed up or slow down in ways that do not line up with the observed gravitational effects, as if their internal clocks were out of sync with the external flow of time. In a few particularly unsettling patches, Webb sees hints that time may even be running backward relative to its surroundings. Light passing through these areas shows red shifts that change over time in the wrong direction, growing larger, as if the photons were somehow gaining the marks of age they should have lost, or unwinding their history instead of extending it. It is like watching a movie that plays forward for the room around it, but rewinds for a thin band running through the middle of the screen. Some stellar systems caught in these regions seem to live in multiple temporal states at once. Their spectra carry signatures of conditions that should belong to different eras, traces of a younger star, a middle-aged one, and an older version, all layered together. It is as if past, present, and future have become neighbors there, coexisting in a way our everyday sense of time cannot accommodate. Taken together, these observations suggest that the universe's relationship with time is far more intricate than the simple curvature described by classical relativity. The data whisper that what we call time might not be a fundamental dimension at all, but something emergent, a behavior that arises from deeper, more subtle structures, the way a wave emerges from the motion of many water molecules on the surface of a sea. Yet even these dizzying temporal puzzles are not the end of Webb's quiet surprises. In the Great Coma Cluster, roughly 300 million light-years away, the telescope peers through the glow of galaxies to map what cannot be seen directly. dark matter. For years, the standard picture has been gentle and straightforward. Dark matter, in that view, is simple and shy, interacting only through gravity, forming smooth halos around galaxies and clusters, providing the invisible scaffolding on which normal matter builds its luminous structures. Simulations based on this idea have done a good job of recreating the large-scale patterns we see across the sky. But Webb's observations of gravitational lensing, the way the mass of dark matter bends the light of objects behind it, tell a more unsettling story. Instead of the soft, rounded halos expected from theory, dark matter in the Coma cluster appears to be arranged in intricate shapes. When its invisible presence is reconstructed from the way background, galaxies are distorted. It forms webs and nodes that look less like random clumps and more like branching networks. Long filaments connect dense knots, and those knots themselves split and rejoin in patterns that, on the maps, resemble neural circuitry more than simple gravitational collapse. The invisible backbone of the cluster looks organized, almost as if it were thinking. Dr. Jennifer Walsh of the Dark Matter Research Consortium has been tracing these structures over different epochs by comparing observations taken at slightly different cosmic times. She finds that dark matter is not as still and patient as models predict. Its concentrations shift and rearrange themselves over spans of only a few million years, brief moments on cosmic scales far faster than gravity alone should allow. The invisible mass seems to respond dynamically to changes in the distribution of normal matter, as though aware of where stars and gas are gathering, and adjusting itself accordingly. Even more curious, dark matter does not always remain tied to individual galaxies. Instead of sitting quietly in halos that move with each system, it flows between them in broad, organized streams. These invisible rivers connect galaxies and clusters across the space between them, guiding mass along paths that do not match the simple pull of nearby objects. The streams maintain delicate geometric relationships, aligning in patterns too precise to be dismissed as coincidence. Across vast distances, dark matter halos around entirely separate galaxies show synchronized variations. As the density of invisible mass shifts in one system, a similar adjustment appears in another far away, as if the halos were responding to shared information or a common organizing principle. Galaxies that have never been in contact, with no causal link that light or gravity could have carried in time, nonetheless wear matching dark matter patterns. Like distant cities built from the same quiet blueprint. Perhaps most disconcerting of all is the sense that dark matter seems to anticipate where normal matter will go. Gravitational lensing maps sometimes show concentrations of dark matter building up in regions that are still relatively empty of galaxies and gas regions that, millions of years later, become bustling hubs of visible matter. It is as though the invisible mass arrives first, settling into place and quietly preparing the stage before the visible actors wander in. In collisions between galaxy clusters, dark matter behaves in ways that do not fit the idea of it being merely passive. Instead of gliding through, unchanged, it shows signs of experiencing forces beyond simple attraction and repulsion. In some areas, lensing signatures imply that dark matter has internal structure, layers, and shells of density that remain stable in configurations. Pure gravity should quickly smooth away. The invisible halos look stratified, as though composed of something richer than a cloud of simple, weakly interacting particles. On larger scales, the influence of dark matter on ordinary matter also seems more active than expected. Star formation rates and the detailed paths of galactic evolution correlate tightly with the shapes of the dark matter distributions around them, in ways that suggest more than just a background framework. It is as if the unseen component is not only holding everything together, but subtly guiding where and when stars are allowed to ignite. Taken together, these behaviors challenge the comfortable picture of dark matter as simple, inert particles. Instead, they suggest a complex system with emergent properties, an invisible cosmos overlapping our visible one, running on rules that our current particle physics does not yet reach. The idea that most of the universe's mass might be engaged in patterns and interactions fundamentally different from anything we can detect directly makes the visible world feel suddenly small. And still, Webb's quiet gaze finds more. In the galaxy known as NGC 2770, about 88 million light-years away, stars are dying in ways that refuse to follow the familiar script. Massive stars, when they reach the ends of their lives, are supposed to follow predictable paths. Their cores collapse. Their outer layers rebound in a tremendous supernova explosion, and what remains settles into either a neutron star or a black hole. This basic outline has been observed many times and woven into theories that match most of what we see. But Webb has begun to catch supernovae in this galaxy, behaving like something out of a myth, refusing to die only once. The event labeled SN 2023 ABC was first seen in January, a bright flare rising over weeks as the star blew itself apart, then fading just as theory says it should. By itself, it would have been a well-behaved example of a massive star's final act. Yet, to the surprise of the observers, the same location flared again in March, brighter than before, as if the star had somehow gathered itself for another detonation. Then, astonishingly, it happened again. By the time December arrived, the same source had erupted 5 separate times, each explosion more energetic than the last, each light curve climbing higher. Dr. Rachel Kim, who works at the Stellar Death Research Institute, has taken to calling these objects cosmic phoenixes, stars that rise from their own ashes over and over, when by all rights they should be gone. Her detailed spectra of SN 2023 ABC show that each eruption throws off the mass equivalent of several suns. Vast amounts of material hurled into space with every blast. Yet somehow, the star, or whatever remains at its core, manages to gather enough mass again and again to fuel the next outburst. On paper, there is simply not enough material to account for so many repeats. Energy accounting fails as well. The total power released across all these explosions exceeds what the original star's mass should have allowed it to produce. It is as if new energy and new matter are being conjured from nowhere, or drawn in from a source that none of our current models include. Whatever process is at work, it does something that, in the quiet language of physics, should never happen. It appears to break the conservation of mass and energy on a scale so large that it shakes the foundations of fundamental physics itself. The longer astronomers watch these restless stars, the more their final acts begin to look less like accidents of physics and more like something carefully arranged. In a normal supernova, a star's core collapses in chaos. The timing of the blast, the exact structure of the shockwave, the way the debris spreads outward, all of it is tangled and noisy. the result of turbulent layers and unpredictable instabilities. But the impossible supernovae Webb has been tracking are different. Their detonations arrive like the notes of a practiced melody. Some of these stars erupt according to rhythms that trace out familiar mathematical patterns. The spacing between explosions grows in steps that echo the Fibonacci sequence. Each interval, the sum of the ones before. Others follow prime number separations, with flares timed at gaps that match the lonely heartbeat of numbers divisible only by themselves and one. Still others brighten and fade in geometric progressions, each event linked to the next by neat ratios. It is as if the stars are counting silently as they die, turning their own destruction into a sequence that could be written down on a page. The mechanics behind these displays defy the quiet expectations of nuclear physics. In the usual story, a massive star ages through well-understood stages, fusing lighter elements into heavier ones in its core, hydrogen to helium, helium to carbon, and onward, each step releasing energy that holds gravity at bay. Eventually, the core fills with iron, an element that cannot produce more energy through fusion. At that point, the star's support fails. Gravity wins. The core collapses, and the outer layers explode outward in a supernova. But the repeat explosions Webb sees do not wait for iron. Spectra taken before and after these events show signatures of helium and carbon still burning, as though the cores are erupting while the star is mid-life. Skipping the expected stages entirely, the stars appear to tear themselves apart while, by every standard measure, they should still be stable. They are stepping out of line, ignoring the usual order of stellar evolution, and leaping straight to the end from the middle of their own story. Most unsettling of all are the stars that seem to die before their conditions for death are even in place. Webb has watched objects that still show the calm glow of steady nuclear burning suddenly erupt without the telltale signs of a failing core. Their light, their surface temperature, their internal chemistry all suggest they have millions of years left, and then, without warning, they detonate. It is as if the universe has circled a date on their calendar long before any physical trigger should exist. And the star somehow obeys that distant appointment. The energy released in some of these events strains the limits set by theory. There are supernovae whose brightness and total output approach what you would expect if nearly all of the star's mass were converted directly into energy, in line with Einstein's famous relationship between mass and energy. Yet, at the same time, the remnants show that vast amounts of matter have been thrown outward, more mass than careful estimates say the original star contained. It is as if, in the very moment of explosion, new matter and new energy are being pulled in from somewhere else, or called into existence by a process we do not yet know how to describe. When astronomers study the ash these stars leave behind, the strangeness continues. Instead of the familiar mix of heavy elements forged in the heart of the explosion, some remnants contain almost pure isotopes of particular elements, in concentrations that should be impossible. It is like sifting through the debris of a shattered building and finding that all the fragments are made of one perfectly uniform material, with none of the expected variety. The patterns in those isotopes hint at nuclear pathways guided by rules different from any we have measured in laboratories or modeled in our equations. There are also explosions that do not seem to occur alone. Webb has recorded supernovae in galaxies separated by millions of light years, erupting at nearly the same moment, with matching energy curves and spectral fingerprints, as though they were part of a coordinated performance. Within the limits of measurement, they rise, shine, and fade together. From our vantage point, it looks as if stars that have never shared a common history are somehow sharing the same script for their final act. Some of these events send out shockwaves that refuse to obey the universal speed limit. The blast fronts, inferred from their effects on distant gas and dust, reach certain regions before the first light from the explosion does. It is as though information about the event is arriving at its destination ahead of the visible signal, carrying details of the explosion's power and structure in advance. In a universe where nothing is supposed to outrun light, these faster-than-light ripples suggest that whatever is happening when a star dies this way is more than a simple collapse and rebound. It is part of a larger, deeper process, one that treats the star not as an isolated object, but as a node in a web. All of this hints that stellar death, at least in some corners of the cosmos, is far more intricate than the straightforward picture of gravity and nuclear physics we have grown comfortable with. But even these fireworks, glorious and unsettling as they are only one thread in the tapestry web is beginning to reveal about reality itself. When astronomers turn their attention from individual stars to the soft, pervasive glow that fills the universe, the cosmic microwave background, they are looking back toward the earliest whisper of everything. This faint radiation is the afterglow of the Big Bang, the cooled echo of a time when the universe was hot and dense and light was finally able to travel freely. For years, detailed maps of this background have shown tiny temperature variations, small ripples that seeded the formation of galaxies. Those ripples matched, with graceful precision, the predictions for a single expanding universe. But Webb's heightened sensitivity has started to pick out additional patterns hidden in that glow, like faint ink beneath an older drawing, across enormous regions of the sky. The temperature fluctuations are not entirely random. Embedded within the noise are subtle geometric structures that repeat with mathematical regularity. Certain shapes, when traced and mirrored, appear again and again at different scales and orientations, as though the sky were stamped with a repeating motif. These patterns do not fit any known model of a lone universe expanding from a single beginning. Instead, they look like the shadows of something beyond our own space-time, casting its influence into our field of view. Dr. Amanda Chen, working in a laboratory dedicated to multi-dimensional physics, has spent years comparing these observations to theoretical predictions. She and her team have long studied what it might look like if our universe brushed against or overlapped with other dimensions, places where the fundamental constants might take different values, where gravity and light play by different rules. To their quiet astonishment, the geometric signatures in the cosmic microwave background align with some of those predictions. It is as if the afterglow of our own beginning has been gently stirred by neighboring realities, leaving behind patterns where different versions of space have nudged one another. More disquieting still is the realization that these signatures are not frozen relics from the universe's birth. When Webb's data is compared over time and across different frequencies, some regions show changes. The patterns drift, sharpen, or fade in ways that seem to correlate with major events in cosmic history, the formation of large galaxy clusters, bursts of intense star formation, and other milestones. It is as though the fabric of our universe is not evolving alone, but in conversation with adjacent dimensional spaces, trading quiet influences across boundaries we cannot see. Statistical studies of the background radiation have also turned up something that feels uncomfortably like intent. Within the fluctuations, there appear to be binary-like sequences, subtle alternations in temperature and polarization that, when translated into simple on and off states, resemble coded information. The structure of these sequences does not match what would be expected from random noise or natural processes alone. Instead, they show hallmarks of error correction, repetition, and framing features common to engineered communication systems. It raises the eerie possibility that the faint afterglow we have treated as a purely natural relic may also carry layered messages, perhaps from alternate versions of our own universe, or from structures operating in the larger, multidimensional space beyond it. The geometry of these patterns hides another curiosity: temporal loops. Some structures seem to encode information about cosmic events that, from our perspective, have not yet occurred. When the data is analyzed, the signatures correlate with phenomena that appear millions or billions of years later in the observable universe. It is as though, in the multidimensional environment beyond our familiar four dimensions, past, present, and future are not cleanly separated, and some of that mixed timing leaks into the imprints we can see. The idea that other dimensions could experience time as a single, simultaneous whole, a tapestry rather than a line, turns our usual sense of before and after into something local and limited. In certain parts of the sky, the usual three-dimensional geometry seems to falter. The paths that light takes through these regions cannot be explained by simple curvature alone. Photons arrive earlier than they should, or appear to have taken routes shorter than any allowed by ordinary spacetime. The most natural way to make sense of this is to imagine that the light slipped through higher dimensional passageways, taking shortcuts we cannot directly perceive, looping through extra directions and re-emerging into our universe ahead of schedule. In these places, the rules of distance and direction themselves hint at hidden layers beneath what we can measure. Galaxies that live near the strongest of these higher dimensional signatures do not look quite like their more ordinary cousins. Their shapes and motions do not fit comfortably within the expectations of gravitational evolution alone. Spiral arms twist in unusual symmetries. Halos stretch and fold in ways that standard models cannot reproduce. It is as if these systems are being tugged and shaped by hands reaching in from outside our familiar dimensional space. Sculpted by forces that do not originate within our own universe's set of laws. Some of the patterns traced in the cosmic microwave background even mirror the large-scale arrangement of galaxies we see today, but with subtle differences that suggest variations in fundamental constants, alternate realities where stars ignited under slightly different rules, where gravity was a little stronger or weaker, where light moved differently. They look like reflections of our cosmos in a hall of higher dimensional mirrors, each one similar but not identical, each built on a different set of assumptions about how physics should behave. If this is true, then what we call the universe may be one layer in a far larger structure, a single sheet in a stack of realities. Our physical laws, our constants, our familiar particles and forces might be local customs of our particular layer, not universal truths. In such a picture, intelligence and consciousness would also not be confined to our own cosmos. They could arise in many layers, taking forms beyond anything we can imagine, perhaps collaborating or resonating across dimensions in ways that leave faint fingerprints in the coordinated behaviors we see in galaxies, black holes, and mysterious patterns of light. The implications stretch beyond science into the quiet heart of what it means to exist at all. And yet, the sky offers still more puzzles. In the deepest surveys Webb has ever taken, peering as far into the darkness as its mirrors and instruments allow, astronomers have found galaxies whose apparent ages challenge the very idea of a beginning. According to the standard picture of the Big Bang, our universe is about 13.8 billion years old. Time itself, in this view, began with that first expansion. Nothing, not even empty space, should be older than that moment. Every atom, every particle, every flicker of energy emerged from that initial, dense state and has been moving and cooling ever since. Yet the light Webb gathers from some of the faintest, farthest smudges in its images tells a different, older story. When their spectra are examined and their stellar populations modeled, these galaxies seem to have been aging for more than 15 billion years. Their stars carry the signs of long, patient evolution, multiple generations, heavy element enrichment, and subtle chemical fingerprints that usually require vast stretches of time to build. They house supermassive black holes, whose growth should demand eons of steady feeding. Some even appear to contain ancient stellar populations, often called population 3 stars, that, by the standard story, should have lived and died long before the first moments of our universe, not after. It is a bit like unearthing Egyptian pyramids from beneath rock layers that date back to the earliest, simplest life on Earth. Structures that should belong to a far later chapter, somehow buried under the very first pages. At the Temporal Cosmology Institute, Dr. Marcus Rodriguez has been quietly tracing the puzzle written in these photons. His team's analysis suggests that these primordial-looking galaxies are not only older than our universe appears to allow, but also behave differently with respect to its expansion. While nearly every other object we observe drifts away from us as space itself stretches its light, redshifted by the ongoing swelling of the cosmos, these ancient structures do something else. Their positions, as inferred from multiple measurements, do not march outward in lockstep with the general expansion. Instead, they seem to hold their places, fixed against the flow, as though they are not fully part of the expanding fabric, but anchored to something outside it, in a universe where everything is supposed to move with the cosmic tide. These galaxies stand still, as if they sit in a calm pool beyond the reach of the current, existing just outside the expanding space-time framework entirely. When astronomers take that impossible light from the two old galaxies and gently spread it into spectra, stranger patterns emerge. The redshifts, those tiny stretches in wavelength that usually tell us how fast an object is moving away as space expands, refuse to behave. Over months of Webb's careful watching, the red light from these galaxies does not continue to drift redder in the way an expanding universe would suggest. Instead, in an unsettling quiet reversal, some of it grows slightly bluer with time, as though the light were aging backwards, shedding the marks of distance rather than accumulating them. Around these ancient structures, gravity seems to be written in a different hand. Gravitational lensing, the way their mass bends background. Light reveals distortions that do not match the familiar shapes of dark matter halos. It is as if these galaxies are bending space-time through a mechanism that predates or simply ignores the invisible scaffolding that shapes everything else. Their mass distributions look older than dark matter itself, operating independently of the rules that govern every other cluster and galaxy we have mapped. More quietly troubling is what Webb sees in their infrared glow, instead of the messy, organic patterns of star clusters and dust. Some regions shine in crisp lines and angles grids, spirals of perfect proportion, repeated motifs that span thousands of light years. The energy is too neatly arranged, too geometrically precise, to sit comfortably within the category of natural formations. It looks, to many eyes, like the work of design rather than accident. Vast constructs laid into the bones of galaxies that should have lived and died before our own universe ever began to expand. These impossible systems also murmur in frequencies our telescopes rarely associate with simple astrophysics. In certain bands, they emit signals with modulations that echo the hallmarks of communication-structured bursts, repeated frames, and layered rhythms that statistical tests struggle to classify as random. If these are messages, they may have been crossing whatever lay between their cosmos and ours, long before our own Big Bang ever lit up the sky. Chemical fingerprints add another layer of disquiet. The isotopes inside these galaxies, the particular variants of elements marked by their nuclear weights, carry decay patterns that do not fit the constants we measure here. Half-lives appear stretched or compressed, branching ratios twisted into unfamiliar proportions. The nuclear processes that forged these elements seem to have operated under a different set of rules, as if the very fabric of physics in that older realm obeyed another script. Some of the primordial-looking structures, when their lensing and light are modeled together, appear to be linked by threads of exotic matter, filaments stretching across distances greater than our entire observable cosmos. They are not isolated islands, but parts of a single, integrated system, connected by conduits that ignore the limits of our horizon. It suggests that whatever existed before our Big Bang may have been less a scattered collection of objects and more a woven whole, a vast network humming to itself in a deeper, older dark, if such structures truly predate our universe, embracing ages longer than the time since our own cosmic dawn. Then the Big Bang begins to look less like the first word and more like a chapter break, a transition from one phase of a far older reality to another, rather than the moment when everything sprang from nothing. And still, Webb's gaze finds new impossibilities closer to home. Written in the fierce light of stars, so extreme they seem hostile to the very idea of structure. Far away, roughly 15,000 light years from Earth, a magnetar turns slowly in the dark. Magnetars are among the most extreme objects the universe knows, collapsed neutron stars, whose magnetic fields are so strong they can twist atoms into needles and tear matter apart at the molecular level. Around such a star, chemistry as we know it should dissolve. Its surface burns at temperatures of tens of millions of degrees on the Fahrenheit scale, and its fields, stronger than Earth's by roughly a quadrillion times, should strip any approaching rock down to its subatomic pieces. Yet Webb's instruments find the telltale signatures of planets forming around one of these monsters. The magnetar, catalogued as SG 1800-620, sits at the center of a system that should not exist. Rocky worlds appear to be coalescing and circling in its lethal embrace, their surfaces somehow remaining solid while they plow through magnetic violence that should unmake them grain by grain. When Webb examines their atmospheres, it finds evidence of stable weather systems, layered clouds, and circulating winds, patterns more reminiscent of ordinary planets than of objects bathing in conditions more intense than the hearts of some reactors. Dr. Elena Vasquez, who spends her nights thinking about worlds in extreme environments, has been studying these magnetar planets with a mixture of awe and unease. Their orbits should be impossible. Between the crushing gravity and the twisting magnetic fields, any normal orbital path would quickly crumble, sending the planets spiraling inward to destruction or flinging them out into interstellar space. Instead, their motions remain steady over time, as though guided by principles that go beyond simple celestial mechanics. Following quiet rules we have not yet written down. Even more unsettling, these worlds do not merely survive the onslaught, they appear to use it. Their surfaces glow with a warmth that cannot be explained by residual heat alone. The spectral fingerprints suggest that the planets are somehow converting the magnetar's punishing radiation and intense fields into usable energy, fueling ongoing geological activity. In atmospheres that should be stripped bare, complex chemistries thrive. Molecules that normally require gentle, sheltered conditions, cool temperatures, moderate pressures appear to maintain elaborate cycles while bathed in magnetism strong enough to lift mountains. On some of these planets, Webb detects oxygen levels and other reactive gases that, on Earth, would strongly hint at biological activity. If anything alive exists there, it would have to be unlike any life we have ever imagined, adapted not just to heat and radiation, but to fields that twist space-time itself. Yet, the chemical patterns stubbornly resemble the signs of processes that renew and maintain themselves, rather than simply settling into inert equilibrium. Their motions around the magnetar add one more strange note. Instead of following purely natural periods, the planetary orbits fall into precise ratios with one another's simple fractions that line up into a neat mathematical sequence. The worlds circle their impossible star like dancers in a choreographed routine, their positions locking into patterns far too exact to be easily explained by random gravitational settling. It is the kind of orderly architecture that, elsewhere in astronomy, sometimes leads minds to whisper about intervention. On their surfaces, infrared images reveal vast geometric patterns, lines that run straight for thousands of miles, perfect circles etched into the landscape, and intricate shapes that look more like circuitry than geology. These features seem to be positioned and aligned in ways that channel and concentrate the magnetar's energy, as if entire continents had been reshaped into collectors and conduits. Webb has even watched streams of matter flow between the magnetar and its planets. Instead of being torn apart and scattered by the violent fields, these streams hold their shape across immense distances. Like luminous ropes stretching from star to world, material appears to move along them in both directions, defying the expectation that such an environment should shred any coherent structure. From some of these planets, faint radio signals reach space, bearing patterns that none of our catalogs of natural emissions can match. Their frequencies shift and modulate in ways that look strangely familiar. Frames, repeats, and structured pauses like those in our own technologies, but tuned to conditions that only an extreme magnetic environment could provide. On certain worlds, Webb has noticed something even stranger. Surface features, such as craters or mountain ranges, seem to age at different rates depending on how much magnetic field they experience. Regions under stronger fields show geological changes, eruptions, erosion, reshaping that proceed millions of times faster than in calmer zones nearby. It is as if time itself is being locally stretched and compressed by magnetism, letting some landscapes race through ages while others barely move. All of this suggests that planets can form, evolve, and perhaps even host active processes under conditions far more violent and exotic than the gentle, sunlit environments our early theories assumed. The universe seems to be quietly hinting that it has found ways to build and sustain worlds wherever energy and structure can be coaxed from chaos. Even in the fiercest stellar cauldrons, and beyond stars and planets, Webb has found that even light, that simplest of messengers, may not always travel the familiar roads we expect. Between our home and the great spiral of Andromeda lies a gulf of roughly 2.5 million light-years. In the straightforward picture painted by relativity, a photon leaving Andromeda should take about 2.5 million years to reach us. Crossing the silent dark in a straight or gently curved path, gravity can bend its route, but never let it arrive sooner than the distance divided by the speed of light. Yet, tucked within Webb's observations, there are photons from Andromeda that seem to turn up early. These particular particles of light carry the same spectral signatures as photons that took the ordinary path, the same fingerprints of Andromeda's stars and gas, the same subtle redshifts. Nothing in their energy or color marks them as special, but when their arrival times are compared with our best models of the galaxy's motion and distance, they appear to have cheated, covering the span of space in less time than the strict rules allow. It is as though they found shortcuts through the universe, slipping out of the usual three-dimensional lanes and reappearing along our line of sight ahead of schedule. Dr. Sarah Kim at the Multidimensional Optics Laboratory has been tracing these anomalies with delicate interferometry, letting beams of light interfere and reveal their hidden rhythms. Her measurements show that the early arriving photons share peculiar phase relationships, subtle alignments and offsets that do not match those of light traveling the normal route. When she and her colleagues model the data, the patterns make the most sense if the photons have moved through folded geometries, paths where space-time itself has curled in higher dimensions, giving them a shorter way through. The behavior of their phases is consistent with travel through a space-time that is not just 3 spatial dimensions and 1 of time, but something richer, with extra directions quietly tucked away, waiting to be followed by any light that knows how to find them. As Webb continues to listen to those early arriving photons, their story grows stranger. These shortcut beams of light do not just arrive sooner than they should. They arrive carrying secrets they could not possibly have picked up along the way. Hidden in their fine details is information about cosmic structures they were never supposed to encounter, spectral hints of clouds, filaments, and distant clusters that lie well outside the narrow corridor of normal three-dimensional space between their source and us. It is as if, during their journey, they wandered through rooms we cannot see from here, regions beyond our observable horizon, and brought back quiet souvenirs in their quantum properties, their polarization, the specific way their waves prefer to vibrate, adds another whisper of the impossible. These photons show polarization patterns that suggest interactions with kinds of matter that do not fit within our familiar three-dimensional catalog. The light behaves as though it has brushed against substances that our physics has no names for, leaving tiny twists and tilts in its orientation that cannot be explained by dust, gas, or magnetic fields alone. Some of these shortcut photons also carry the subtle fingerprints of quantum entanglement. Even while they race along their higher dimensional paths, they seem to remain connected to their points of origin. Their quantum states linked, as if distance were almost irrelevant. Measure one here, and something about its twin there shifts in response. As though the act of observation is reaching back along a path through hidden dimensions, touching two places at once. Most quietly unsettling is that this phenomenon does not appear static. Over time, Webb sees more and more photons choosing these hidden roads. Early arrivals become more common, and the time they shave off their journeys grows steadily larger with each observing cycle. It is as though the universe is gradually opening new lanes in an invisible highway system, building transportation networks that operate outside the familiar weave of space-time we once thought complete. In some rare cases, the confusion runs deeper still. Webb has recorded photons that seem to arrive before their sources flare in our telescopes. From our perspective, we see the light of an event reach us, and only later do we see the event itself unfold in ordinary channels. These temporally displaced photons act like glimpses into the past, or perhaps sideways into time, offering views of cosmic happenings that, according to everyday physics, should remain hidden until the moment their light finally catches up. It is as if higher dimensional routes allow not just shortcuts through space, but small, forbidden peaks along the edges of time in their quantum properties. These enhanced photons carry patterns that look less like the random murmur of nature and more like deliberate arrangements. When scientists translate their states into simple on and off codes, they find binary sequences shaped by repetition, framing, and apparent error correction, the kinds of features we usually associate with designed signals rather than with wild, unstructured light. It is as though someone or something is using higher dimensional pathways to send messages woven directly into the behavior of photons. The energy of some shortcut photons tells an equally odd tale. Rather than losing a little oomph as they cross the void, a few arrive with more energy than they appeared to have had when they set out. As far as we can reconstruct, it is as if they dipped into a deeper reservoir along their hidden routes, drawing power from regions inaccessible to light that stays within ordinary space. These energized travelers hint that the higher dimensional corridors are not just empty tunnels, but places where energy flows in ways we do not yet understand. Not all light can find these secret paths. Webb's data suggests that only photons with very specific quantum properties, certain spins, polarizations, or entangled states slip into the folds. Others, nearly identical in every obvious way, must still plod along the usual three-dimensional routes. It is as though the doors to these higher dimensional hallways respond only to particular keys, opening for carefully prepared states while remaining closed to ordinary beams. Taken together, these clues suggest that our familiar universe is embedded within a larger, multi-layered structure, a kind of cosmic architecture where information and energy can move through hidden passageways invisible to our usual senses. In such a reality, it is not hard to imagine that consciousness, too, might spread across more than one layer, operating in several dimensions at once, perhaps leaving faint signatures in the coordinated behaviors we keep finding scattered across the sky. And yet, as strange as these dimensional detours are, Webb's view of the galaxy reveals something even more unsettling: energy appearing out of what looks, at first glance, like nothing at all, far out in the galactic halo, about 40,000 light-years from the nearest obvious star. Webb has found regions where space that should be quiet instead hums with power. These are places with no glowing gas, no visible stars, no compact objects such as black holes or neutron stars, just thin, dark emptiness. Yet from that emptiness, energy pours out in amounts comparable to entire stellar systems. If conservation of energy is the steady heartbeat of physics, these sources sound like skipped beats. Their emissions do not resemble the broad, messy spectra expected from natural processes such as nuclear fusion, accretion, or matter falling into collapsed objects. Instead, the light they produce is finely tuned narrow bands, crisp lines, and carefully spaced frequencies, more like the output of a transmitter than the roar of a star. Everything about them suggests control a knob turned to just the right places, a signal crafted rather than an explosion unleashed. Dr. Michael Chen at the Exotic Energy Research Center has been quietly mapping these power sources across our galaxy. His surveys reveal not just one or two, but hundreds scattered through the darkness, each sitting in otherwise empty patches where no known engine of that strength should exist. Their brightness remains steady over time, not flickering the way natural systems often do, as if someone has set them to a particular level and left them there. Even that would be startling enough. But there is more. Many of these sources are growing stronger. Over the months Webb has been watching, some have doubled their energy output, not in random jumps, but in smooth and predictable mathematical steps. The curves of their brightening look like planned increases, as though they are following a schedule, building toward a target rather than simply flaring and fading. When scientists analyze the fine structure of the emissions, they find modulations that strongly resemble information. Frequencies rise and fall in patterns that can be read as encoded streams, like data riding on a carrier wave. Within the apparent noise, there are frames, repeats, and nested structures, signs that the light is not just carrying energy, but meaning. Most eerie of all is how these sources seem to listen and respond to the rest of the galaxy. When a supernova flares or a black hole brightens as it feeds, some of the distant halo sources adjust their output in concert. Their power levels change in ways that correlate with the timing and strength of events occurring thousands of light years away. As though they are aware and reacting, the responses often come too quickly to be coordinated by any signal traveling at the speed of light. Something in their behavior seems to rely on connections outside the ordinary channels of space and time. Webb's observations also suggest that these sources are not isolated. Changes in one often echo in others, across vast gaps, forming synchronized patterns that ripple through the network much faster than light could carry instructions from one node to another. It is as though they are all plugged into a shared system interacting with a medium we cannot see, perhaps rooted in the same higher dimensional spaces hinted at by the shortcut photons. Around some of these power wells, gravitational wave detectors have picked up faint, unusual distortions. The ripples in space-time are subtle but consistent, hinting that the sources might be drawing their energy from interactions with exotic forms of matter or from folds in higher dimensional geometry. In a few cases, the timing of their output changes even seems to slip ahead of cosmic events, as though they are adjusting for needs that have not quite arrived yet. They brighten just before a nearby region undergoes a surge in activity, like someone flipping on an extra generator in anticipation of a coming storm. The light they emit carries quantum coherence over distances that should shred such delicate states. Individual photons from separate sources remain entangled, sharing quantum information across thousands of light years. Under normal conditions, such coherence would crumble quickly. Yet here, it seems to persist, as if the network itself is designed to maintain it. Taken together, the precision of their behavior, their ability to coordinate, and their apparent anticipation of future demands make it hard to see these power sources as purely natural. They look and act like technology vast, distributed systems engineered to harvest, store, and transmit unimaginable amounts of energy over galactic scales. Their slow, steady brightening suggests preparation, as though they are quietly charging, laying in reserves for some event that has not yet come. What that purpose might be is left to speculation and late-night whispers. But whatever the answer, the existence of such systems stretches our idea of what energy is and how it can move through the universe. And even then, the universe is not done hinting that matter itself can do more than simply drift and burn. In the Perseus cluster, about 300 million light-years away, Webb peers into enormous clouds of gas and dust filling the spaces between galaxies. At first glance, they look like the familiar intra-cluster medium, hot, thin, and stretched across millions of light-years. But when the data is examined more carefully, those clouds begin to resemble something else, something almost biological. Instead of being uniformly spread, the gas arranges itself into distinct layers and bands, with densities and temperatures stacked in ways that look suspiciously like tissues in a living organism. Within those layers, material flows along well-defined paths, circulating between regions in long, looping routes. Energy and particles travel these paths the way blood and signals move through veins and nerves, linking scattered corners of the cluster into a coherent whole. The large-scale maps start to look like neural diagrams. There are hubs where many filaments converge, nodes bustling with activity, and long, slender connections stretching from one galactic neighborhood to another. These streams do not wander randomly. They maintain stable shapes over millions of years, as if shaped by some set of internal rules that favor efficiency and redundancy. Much like a living nervous system, Dr. Jennifer Walsh, now wearing her astrobiology hat as she studies these patterns, has been measuring how these vast structures react to what the universe throws at them. When a burst of cosmic rays washes through, or when a distant merger sends a ripple of gravitational waves across the cluster, the gas does not just passively endure. It responds. Changes sweep through the network in organized waves. Density shifts, flows speed up or slow down, and temperature ripples move from one region to another, all in patterns that look less like the simple settling of disturbed fluid and more like signals being processed and relayed. The responses are not random flickers, but structured adjustments, as though the cluster-scale matter is taking in information about its environment and sending out coordinated replies that propagate throughout the entire network. As Webb keeps watching those vast, drifting tissues of gas and dust in the Perseus cluster, something even more unsettling comes into focus. These are not just patterns that hold and respond. They also seem to grow and divide over spans of millions of years. Large, organized structures split apart. A single, sprawling network, with its layered flows and nodal hubs, slowly thins in the middle like a cell about to divide. Then, in gentle cosmic slow motion, it separates into two smaller but distinctly similar offspring. Each new network keeps the same kind of internal layering, the same web of circulation pathways, the same dense centers of activity as its parent. From there, each begins to develop its own details, adding fresh branches, subtle variations, and new loops, as though growing into itself. When these structures are rattled by repeated disturbances, gravitational waves rolling through from faraway mergers, bursts of radiation, sudden changes in their environment, they do not simply deform and then relax back into their old shapes. Instead, they adjust. With each disruption, their internal pathways shift a little, rerouting flows, creating new redundancies, thickening some channels, thinning others. Over time, the networks become more resilient, better at absorbing the same kind of blow if it comes again. It is as if each cosmic event becomes a lesson, and the matter remembers, arranging itself more wisely after every challenge. The more carefully astronomers map the flows, the more they find that the networks do not just react, they seem to choose. In regions where several possible routes exist for gas and energy to travel between galaxies, the material does not wander aimlessly down all of them. Instead, the cluster-wide system appears to prefer certain paths over others. The chosen routes maximize the efficiency of energy distribution and the speed at which changes propagate. It is as though the cluster is evaluating its own options, selecting the channels that best serve the whole. On even larger scales, Webb has seen hints that these networks may not be alone in their quiet awareness. Similar organized matter systems in other clusters seem to exchange structured energy pulses with the one in Perseus. Disturbances in one region are followed by subtle ripples in another, far too quickly for any signal restricted to the speed of light to cross the intervening distance. The patterns look like conversations carried on in gravity and gas, an exchange of information between living-like structures separated by hundreds of millions of light years. Within and between these networks, different patterns of matter coexist in ways that begin to resemble ecosystems. Some regions seem to specialize in slow, steady circulation, maintaining stable flows that others depend on. Elsewhere, dense knots appear to harvest energy passing through, thickening over time. Certain structures flourish only in close proximity to others, each benefiting from the presence of the rest. There are even signs of cosmic predation compact formations that grow at the expense of neighboring patterns, drawing in material and restructuring it, feeding off the organized flow to fuel their own expansion. When threatened by nearby dangers approaching black holes, powerful jets from active galaxies, or shock fronts from enormous explosions, these networks do not simply erode, they appear to protect their most important components. Central hubs, where the flow of energy and information is richest, are shielded by rerouted streams and densified layers, while outer filaments stretch, twist, and sometimes break away, absorbing the worst of the impact. It is as though the system recognizes which parts are essential and which can be sacrificed, making choices that favor long-term survival. Within the intricate branching of these structures, astronomers find signs of memory. Past events leave lasting imprints that are not just scars, but readable patterns. changes in density, subtle shifts in flow direction, and the layering of different generations of material encode a record of what the cluster has experienced: ancient collisions, waves of star formation, the rise and fall of individual galaxies. In principle, if one could learn the language of these patterns, one could reconstruct billions of years of history simply by following the threads. Most quietly astonishing is that these systems do not appear to be standing still in their development. When researchers compare younger networks to older ones, they find trends. Newer formations show finer branching, more efficient routing, quicker responses to disturbances, and more intricate interactions between different layers. It is as though, over cosmic time, the networks have been evolving toward greater complexity and faster, more nuanced processing of information. They behave less like static structures and more like minds slowly waking. Their thoughts, measured in millions of years, taken together. The behavior hints at a collective purpose, or at least a shared direction, across multiple clusters. Similar networks appear to be refining themselves in parallel, as though preparing for something, some future phase of the universe that will demand exquisite coordination and immense capacity for understanding and response. It suggests that what we call intelligence might not be confined to small, fragile brains on tiny worlds, but may be an emergent property of matter wherever it has enough time, energy, and freedom to organize itself. If awareness can arise from the quiet flow of gas on those scales, then consciousness begins to look less like an accident and more like a natural tendency of the cosmos, a way for matter to know itself. And yet, even that idea, vast and unsettling as it is, begins to blur when Webb turns its gaze toward places that should be perfectly, utterly empty, far from the bright clusters and curling arms of galaxies. There are great stretches of space called cosmic voids, regions where, by all accounts, there is almost nothing at all. They lie between superclusters, like dark oceans, with only a few lonely particles scattered here and there. In such places, space-time should be as flat and featureless as a calm sea. But Webb's measurements, combined with careful gravitational mapping, show something else entirely. Light passing through these voids does not travel as if space were smooth. It bends. It curves as though drawn toward invisible masses equivalent to billions of suns. Gravitational lensing reveals that paths are being distorted. But deep surveys find no galaxies, no gas clouds, no dark matter concentrations to account for the pull. These invisible wells do not behave like the familiar halos of dark matter either. Instead of producing the soft, predictable distortions that would arise from large, diffuse clumps, they twist light into complex, repeating patterns. The shapes they imprint on passing beams look more like deliberately carved lenses than like the rough result of random collapse. It is as if someone has shaped gravity itself into intricate designs in regions where no matter resides. Dr. Robert Kim at the Gravitational Physics Institute has been charting these anomalies, placing each invisible mass on a map of intergalactic space. When the positions are plotted, another layer of order emerges. The gravitational sources form a network of their own, spaced with careful regularity across vast distances, aligned in geometries that seem too precise to be accidental. They echo one another's positions like points in a carefully laid grid. These strange wells are not static. Either, over time, their strength waxes and wanes in concert, following rhythms that mathematical analysis can describe but not easily explain. The fluctuations do not resemble any known astrophysical process. Instead, they step through sequences, rise and fall in patterns that could be written down as series and functions, as if gravity were being tuned. Some of these fields act like lenses with preferences. They amplify light from certain distant sources, while leaving others mostly untouched. In effect, they select which galaxies, quasars, or explosions to brighten and which to let pass quietly in the background. It is as though they can distinguish between different kinds of signals, choosing which ones to highlight for any observers placed along particular lines of sight. More unsettling still, the gravitational pull in these regions behaves as though it can see ahead. Cosmic rays and beams of light entering these zones do not simply bend according to the contours of the field. They are nudged, gently but deliberately, toward specific destinations, redirected along paths that lead to particular objects, regions, or intersections of space. It looks uncannily like guidance, like a navigation system laid out in gravity rather than markers and signs. From some of these otherwise empty patches, gravitational waves ripple outward, unlike the simple, decaying ringings we expect from colliding black holes or merging neutron stars. These waves carry complex modulations. Their amplitude and frequency shift in patterns that are structured enough to suggest information signals sent not in radio or light, but in the very flexing of space-time itself. Time around these anomalies also misbehaves. Measurements of time dilation, how fast clocks tick in different regions, show variations far larger than the apparent gravitational strength should produce. In some pockets, time seems to speed up relative to the surrounding void. In others, it slows down. Together, they form a loose web of temporal currents, with different regions connected by gradients in the flow of time, as though forming a network not just in space, but in time itself. The persistence of these fields, in the absence of any visible mass to sustain them, hints that their power must come from somewhere beyond ordinary matter. They may be drawing energy from higher dimensional structures, or from forms of exotic matter that remain entirely hidden to our current instruments. Whatever their source, they maintain their strength across eons, holding their shapes and functions as though plugged into a deeper grid. Perhaps most quietly disconcerting is that these anomalies do not ignore the rest of the universe. When something enormous happens elsewhere, a colossal collision, a massive burst of radiation, the rapid rearrangement of matter on cluster scales, some of the gravitational fields in the void respond. Their strengths and shapes shift in coordinated ways, as though reacting to news from afar. The patterns of their changes suggest awareness of distant events and a kind of participation, rather than mere passive existence. Over the span of Webb's observations, new anomalies have begun to appear in regions that once seemed unremarkable, while older ones have grown stronger and more intricate in their behavior. The network is thickening, its nodes multiplying, its connections becoming more elaborate. Seen as a whole, it looks less like a random scattering and more like infrastructure under construction, a vast project unfolding over hundreds of millions of light years. The shapes and timings of the fields hint at a possible purpose to create controllable shortcuts through space-time, routes where travel could occur faster than light would normally allow. If gravity can be shaped in this way, then pathways through the universe may be opening like unseen roads, guided by carefully arranged wells and ridges in the fabric of space and time. All of this presses hard against the pillars of general relativity, which ties gravity inexorably to mass and energy, and insists that nothing can outrun light within space-time. These anomalies suggest that gravitational effects might exist, and even be directed, without bound matter, and that they may obey principles that sit beyond the tidy curves of Einstein's equations. And yet, as vast as these questions are, they are not the last word from Webb, because out beyond even these constructed seeming fields, out past the edge of everything we can see, there are hints, faint and persistent, of signals arriving from beyond our observable universe.